Uh,
Okay, so good afternoon, everyone. In our last lecture or in our previous lecture, we have started the chapter number or second part of chapter number 2, that is nothing but the vapor absorption refrigeration system. And in that vapor absorption refrigeration system, we have seen mainly how that vapor absorption refrigeration system is differ from the vapor compression refrigeration system. So as we are knowing that when we are going to replace compressor of vapor compression refrigeration system by absorber, pump, generator and pressure reducing valve, then that vapor compression refrigeration system can be called as the vapor absorbent or vapor absorption refrigeration system. So in case of vapor absorption refrigeration system, the working fluid will be two. Out of that, one will be acting as a absorbent and another one will be acting as a refrigerant. So in case of aqua ammonia vapor absorption refrigeration system, we have seen the absorbent is acting or water is acting as an absorbent, whereas ammonia is acting as a refrigerant. So whatever ammonia is there, ammonia is circulating throughout the system, whereas absorbent water is circulating only through the device called as the absorber, pump, generator and pressure reducing valve. So there are some practical difficulties. There are some practical difficulties to use that vapor absorb simple aqua ammonia vapor absorption refrigeration system in practical application. So we need to do some modification in that simple aqua ammonia vapor absorption refrigeration system. So after adding some of the accessories, so which accessories we are adding? First accessory is nothing but analyzer. Second one is nothing but a rectifier, and third one is nothing but the heat exchanger. So by addition of these accessories, we can make that aqua ammonia vapor absorption refrigeration system as a practical aqua ammonia vapor absorption system. So we have also seen the working principle of that practical aqua ammonia vapor absorption refrigeration system. Now the next point or the next part which we have to see, that is nothing but what is the actual difference between vapor compression refrigeration system and vapor absorption refrigeration system. So we'll see that difference between vapor absorption and vapor compression refrigeration system. So in that difference, the first difference, or we can make the first difference based on the energy input. We can make the first difference based on the energy input. So which type of energy we are supplying to that VCRS and VARS? Depending upon that, we can differentiate that VCRS and VARS. So as we are knowing that in case of vapor compression refrigeration system, we are using the compressor as the main part. And to run that compressor, we require the electrical energy or we require the mechanical energy. So whatever electric energy or mechanical energy is there, that is in the form of high grade energy. So in case of VCRS system, to run the compressor, we require to supply high grade energy that may be either electrical or mechanical energy. But in case of vapor absorption refrigeration system, as we are replacing compressor, by absorber, pump, generator and pressure reducing valve. So in case of generator, we are supplying the heat in the form of low grade energy, or we are supplying the heat which may be exhaust from the steam or IC engine that can be used from the solar heat also. And only pump is there which is having very less moving parts, and that pump can be operated with the help of solar system also. So here in case of vapor absorption refrigeration system, the energy which we are using, that is nothing but the low grade energy, and that low grade energy is in the form of waste heat from the furnace, as well as that may be exhaust steam or that may be exhaust heat which is coming from the IC engine or any of the power plant, or we can also use the solar heat or solar power for its operation. So that is the first difference between vapor compression and vapor absorption refrigeration system. Now second difference is based on the moving part. Second difference is based on the moving part. So in case of vapor compression refrigeration system, in case of vapor compression refrigeration system, the compressor is consisting of number of moving parts. Compressor is consisting of number of moving parts, and it can be driven by motor, electrical motor or engine. So as that compressor is consisting of number of moving parts, that's why the chances of leakage of refrigerant, the chances of leakage of refrigerant in case of vapor compression refrigeration systems are much more. Whereas in case of vapor absorption refrigeration system, only moving part is nothing but the small pump, and function of that small pump will be to take the or to circulate the strong aqua ammonia solution from absorbent or from absorber to the generator and to increase its pressure. So that pump will consisting of small number of moving parts. That's why here, as that pump is having the small number of moving parts, that's why that can be run with smoothly, as well as the chances of leakage of refrigerant in case of vapor absorption refrigeration system as compared to vapor compression refrigeration system will be very much less. Then third one is corresponding to the third point is corresponding to the load variation. Third point is corresponding to the load variation. So here, in case of vapor compression refrigeration system, in case of vapor compression refrigeration system, suppose inside the evaporator, we are not keeping any type of load. That means for poor load condition or for partial load condition, for poor load condition or for partial load condition, the performance of vapor compression refrigeration system for poor load or for partial load condition, the performance of vapor compression refrigeration system is very poor. Why this is so? Because we can't change or we can't adjust the mass of refrigerant which is circulating through the vapor compression refrigeration system. So whatever amount of refrigerant we are filling inside the vapor compression refrigeration system, all the refrigerant, all the time we have to circulate that all the refrigerant which is available in that vapor compression refrigeration system. So if load will be less inside the evaporator, then here that inside the evaporator, that refrigerant, mass of refrigerant will absorb less amount of heat, and because of absorption of less amount of heat, the performance, because amount of power supplied or amount of work supplied to compress that refrigerant is same, because there will not be change in amount of work supplied, but amount of heat absorbed inside the evaporator will go on changing because of poor load condition, and hence it will affect on the poor or it will affect on the performance of that vapor compression refrigeration system. But in case of vapor absorption refrigeration system, there how much amount of mass of refrigerant we have to circulate through the system, that is totally depend on us. How that is totally depend on us? Here, if you take the example, here, if the load inside the evaporator is very less, then here by changing or by controlling the amount of heat supplied to the generator, here I can change or here I can control how much mass of refrigerant I am circulating through the system. जर ह्या ठिकाणचा इव्हापरेटर मधला लोडच कमी असेल तर इव्हापरेटरचा लोड कमी असल्यामुळे काय करणार आहे मी ह्या ठिकाणी जनरेटरला दिली जाणारी हीट जी आहे ती काय करणार आहे मी कमी करणार आहे, आणि जनरेटरला दिली जाणारी हीट कमी केल्यामुळे काय होणार आहे, ह्या ठिकाणी थोड्याच अमोनियाचं कन्व्हर्जन कशामध्ये होणार आहे, अमोनिया व्हेपर मध्ये होणार आहे. त्यामुळे ह्या ठिकाणी मास ऑफ अमोनिया व्हेपर किंवा मास ऑफ रेफ्रिजरंट जो आहे तो काय होणार आहे, चेंज होणार आहे किंवा कमी होणार आहे. आणि मास ऑफ रेफ्रिजरंट कमी झाल्यामुळं तो कमी मास ऑफ रेफ्रिजरंट जो आहे तो कमीच हीट ऍब्सॉर्ब करणार आहे. त्यामुळे हियर देयर विल नॉट बी एनी ऍडव्हर्स इफेक्ट any adverse effect in case of vapor absorption refrigeration system for the poor load condition or partial load condition. But here instead of vapor absorption, या ठिकाणी vapor absorption च्या ऐवजी जर vapor compression असते, vapor absorption च्या जागी जर vapor compression असते, तर ह्या ठिकाणी जर कमी लोड असता, इव्हॅपोरेटर मध्ये जर कमी लोड असता, तर त्या ठिकाणी चान्सेस काय होते, कमी हीट ऍब्झॉर्ब केली असती आणि कमी हीट ऍब्झॉर्ब केल्यामुळे त्या ठिकाणी लिक्विड अमोनिया अलॉंग विथ वेपर किंवा लिक्विड वेपर मिक्सचर बाहेर आलं असतं. इव्हॅपोरेटरच्या बाहेर लिक्विड वेपर मिक्सचर आलं असतं, कारण की कम्प्लीट लिक्विडचं कन्वर्जन वेपर मध्ये झालं नसतं, कारण की तेवढी अमाऊंट ऑफ हीट ऍब्झॉर्ब केलेली नाही. आणि जर लिक्विड वेपर मिक्सचर आलं असतं आणि ते जर आपण कॉम्प्रेसरला दिलं असतं, तर त्या ठिकाणी कॉम्प्रेसरचं फंक्शन जे आहे किंवा कॉम्प्रेसरचा परफॉर्मन्स जो आहे तो काय झाला असता, बिघडला असता. पण ह्या ठिकाणी जरी तुमच्या आउटलेट ऑफ इव्हॅपोरेटरला लिक्विड वेपर मिक्सचर आलं, त्या अमोनियाचं लिक्विड वेपर मिक्सचर आलं, तरी पण ह्याचा परफॉर्मन्स जो आहे तो चेंज होणार नाही किंवा त्याचा ऍडव्हर्स इफेक्ट त्या सिस्टमवरती काही होणार नाही. कारण की जरी ह्या ठिकाणी इव्हॅपोरेटरच्या आउटलेटला तुमच्याकडे लिक्विड वेपर मिक्सचर आलं, तरी ह्या ठिकाणी काय होणार आहे, the liquid vapor mixture of ammonia will get absorbed by or with the help of weak aqua ammonia solution, and that will automatically will get converted into liquid aqua ammonia solution. So here you have to keep in mind that load variation. So in case of vapor compression refrigeration system, the performance of vapor compression refrigeration system will be very poor, or that performance will goes on decreasing at partial load condition. Whereas in case of vapor absorption refrigeration system, as we can regulate the mass of refrigerant circulating through the system with the help of amount of heat supplied inside the generator, that's why performance of vapor absorption system will not change with load variation. Then next point, based on which we can differentiate vapor compression and vapor absorption refrigeration system, is nothing but the evaporator exit. So just now I have told you. So here it is always desirable to have the superheated vapor before leaving the evaporator. That means before entering to the compressor, always we should ensure that the refrigerant is in the either superheated or saturated case. But if there will be the poor or if there will be the partial load, then there may be the chances that refrigerant will come in the form of liquid plus vapor mixture, and if that liquid plus vapor mixture will be given to the compressor, then performance of compressor will go on decreasing. So in case of vapor compression refrigeration system, it is always desirable to have the superheat vapor before leaving the evaporator, so no liquid can enter into the compressor. But in case of vapor absorption refrigeration system, though you are getting outlet of evaporator as a liquid plus vapor mixture, then also it will not have any bad effect on the system. Except reduce of the refrigerating effect. कारण की त्या ठिकाणी आउटलेट ऑफ इव्हॅपोरेटर आपण कशाला कनेक्ट केलेला आहे, ऍब्झॉर्बरला कनेक्ट केलेलं आहे, आणि ऍब्झॉर्बर मध्ये आपलं काय आपण काय करतोय, जे काय वेपर रेफ्रिजरंट होतं त्याचं कन्वर्जन लिक्विड मध्येच करतोय. त्यामुळे त्या ठिकाणी वेपर ऍब्झॉर्प्शन रेफ्रिजरेशन सिस्टीम मध्ये असं काय रूल नाही की बाबा आउटलेट ऑफ इव्हॅपोरेटर ऑलवेज वी शुड हॅव द सुपरहीटेड और सॅच्युरेटेड वेपर. If that will be liquid plus vapor mixture also, then that can also be desirable. But in that case, the system performance or the refrigerating effect will go on decreasing. So this was the fourth point. Now next point is related to the COP. So vapor compression refrigeration system will have the excellent COP. Whereas vapor absorption refrigeration system will have the poor COP as compared to vapor compression. It is not the case that vapor absorption system is having the poor COP, but as compared to PCRS system, the COP of PRS system is less. Then from the point of capacity of the vapor compression and vapor absorption refrigeration system, so we cannot build the PCRS system having capacity more than 1000 PR. So it is for single compression system, it is not possible to have system. It is not possible to have system with more than 1000 TR capacity. But in case of vapor absorption refrigeration system, we can build the capacity well above 1000 TR. So whatever application of that VCRS and VARS will be there. So VARS system will be mainly used in case of air conditioning plant. VARS system, that is vapor absorption refrigeration system, will be mainly used in case of air conditioning plant, which is having the capacity 200 TR or more than 200 TR. That can be increased above 1000 TR also. But VCRS system is there, so we can use the VCRS system for domestic as well as industrial purposes, where capacity of the plant is below 200 TR capacity. Okay. Now, with respect to refrigerant, in case of VCRS system, we can use any type of refrigerant. That refrigerant may be halocarbon refrigerant, azeotropy refrigerant, inorganic refrigerant, or hydrocarbon refrigerant. But most commonly used refrigerants are halocarbon refrigerant, and out of that halocarbon refrigerant, most commonly used refrigerant are nothing but CFC type of refrigerant, then HFC type of refrigerant. CFC means chlorofluorocarbon, HFC means hydrochlorofluorocarbon, and last one is nothing but the hydrochlorofluorocarbon, HCFC type of refrigerant. So in case of VCRS system, we can use halocarbon, hydrocarbon, azeotropy, as well as inorganic refrigerant, but most commonly used refrigerant are halocarbon, and out of that halocarbon, CFC, HFC, and HCFC type of refrigerant we are using in case of vapor compression refrigeration system. But in case of vapor absorption refrigeration system, we are using either water or ammonia as a refrigerant. आता आपण जे काही सिंपल वेपर कॉम्प्रेशन रेफ्रिजरेशन सिस्टम जे काय आपण aqua ammonia vapor absorption refrigeration system बघितली किंवा प्रॅक्टिकल aqua ammonia vapor absorption refrigeration system बघितली. तर त्या दोन्ही सिस्टीम मध्ये aqua ammonia as well as practical aqua ammonia vapor absorption refrigeration system, water was used as an absorbent and ammonia was used as a refrigerant. त्या केस मध्ये रेफ्रिजरंट काय यूज केला होता, अमोनिया एज अ रेफ्रिजरंट यूज केला होता. आता ह्यानंतर आपण फ्री फ्लूइड रेफ्रिजरेशन सिस्टीम, त्याला आपण इलेक्ट्रोलक्स रेफ्रिजरेशन सिस्टीम म्हणणार आहे, ती बघणार आहे. त्या सिस्टीम मध्ये पण आपण अमोनिया एज अ रेफ्रिजरंट यूज करणार आहे. पण त्यानंतर लास्ट सिस्टीम जे आहे दॅट इज नथिंग बट LIVR रेफ्रिजरेशन सिस्टीम, लिथियम ब्रोमाइड vapor absorption refrigeration system. In that LIVR vapor absorption refrigeration system, we are going to use LIVR as an absorbent and water as a refrigerant. म्हणजे मोस्ट कॉमनली तुमची aqua ammonia असू द्या किंवा इलेक्ट्रोलक्स रेफ्रिजरेशन असू द्या, त्या ठिकाणी आपण अमोनिया एज अ रेफ्रिजरंट यूज करतोय आणि फक्त LIVR रेफ्रिजरेशन सिस्टीम मध्ये वॉटर एज अ रेफ्रिजरंट यूज करतोय. So for multiple choice question, this question may be asked, that is in case of LIVR vapor absorption refrigeration system, dash dash is used as a refrigerant or dash dash is used as a absorbent, likewise. Okay, then last point is corresponding to the lowest temperature. So as I have mentioned you, we can use the vapor compression refrigeration system for domestic as well as industrial application where capacity is less than 200 TR. So with the help of VCRS system, we can maintain the temperature or we can lower the temperature up to -150 degrees centigrade or even less than -150 degrees centigrade. So with the help of cascading, so whatever next chapter will be there, multi-pressure system, where you will come to know what is by cascading. So with the help of cascading or with the help of VCRS system, we can lower the temperature below 0 degrees centigrade, and that can be lowered up to -150 or even less than -150 degrees centigrade. So whatever -150 degrees centigrade temperature range is there, so below -150 degrees centigrade temperature, whatever term will be there or whatever application will be there, that will be called as a cryogenic. So we are having separate topic related to cryogenic. So we'll see during that topic. But as we have mentioned, the application of vapor absorption refrigeration system. So vapor absorption refrigeration system is mainly used in case of air conditioning plant. So the minimum temperature or the lowest temperature which we can attain or which we can achieve is above 0 degrees centigrade in case of vapor absorption refrigeration system. So this is the basic difference between vapor compression refrigeration system and vapor absorption refrigeration system. Have you understood? Yes or no? Write in the chat box. Have you understood that basic difference between vapor compression and vapor absorption? Is there any query, any question related to vapor compression and vapor absorption refrigeration system, or sorry, difference between vapor compression and vapor absorption refrigeration system? If you are having any query, any question, you can ask me. Is there? Query, question? Okay. Now, second last system related to vapor absorption refrigeration system is called as a Electrolux refrigeration system, that is also called as a three-fluid absorption system. Electrolux refrigeration system, that is also called as a three-fluid vapor absorption refrigeration system. Now, why this system is called as a three-fluid vapor absorption refrigeration system? Why this system is called as a three-fluid vapor absorption refrigeration system? Because whatever number of fluid we are using in this system are nothing but three, and those are nothing but, first one is nothing but ammonia. Here, to have the working of this system, we will have the ammonia, then water, ammonia, after that water, and last one or last fluid will be the hydrogen. So we are using this three fluid. We are using ammonia, water, and hydrogen to have the working of that Electrolux refrigeration system. That's why this Electrolux refrigeration system is also called as the three-fluid vapor absorption refrigeration system. So out of this three fluid, whatever ammonia is there, that ammonia is used as a refrigerant. Ammonia is used as a refrigerant. Whatever water is there, that water is being used as a absorbent. Water is used as a absorbent, and whatever inert hydrogen is there, so inert hydrogen will be used as a catalyst. So we are knowing the meaning of catalyst. What is the meaning of catalyst? So in the chemistry term, you might be knowing what is meant by catalyst. Catalyst is nothing but one substance which can increase the rate of reaction, without actual taking part inside that reaction, or without actually taking part in the chemical reaction. So that will be called as a catalyst. So in case of Electrolux refrigeration system, or in case of three-fluid refrigeration system, whatever fluid we are using, that are nothing but ammonia. Second one is nothing but hydrogen. Ammonia. Second one is nothing but water, and third one is nothing but the hydrogen. Out of that, ammonia is used as a refrigerant, water is used as an absorbent, and third one is nothing but hydrogen, that will be used as a catalyst. Now, whatever this Electrolux refrigeration system is there, so that Electrolux refrigeration system is modification. It's modification of the aqua ammonia vapor absorption system. So we are knowing aqua ammonia vapor absorption system. So this was the aqua ammonia vapor absorption system. So here, as we are saying that the main purpose of using vapor absorption refrigeration system is to eliminate the use of high grade in electricity or high grade energy. Main purpose of using. So this is the diagram of simple aqua ammonia vapor absorption refrigeration system. So as we are telling that the main purpose of using any of the vapor absorption refrigeration system is to eliminate the use of high grade energy for running of that vapor for running of that refrigeration system. And second point is to eliminate the moving part, so that as we are eliminating the moving part, that's why the chances of leakage of refrigerant is also goes on decreasing. So here, in case of vapor absorption refrigeration system, we are using the pump. So though the size of pump is less, then also for working of that pump, somewhat amount of electric supply we require to give, or somewhat amount of high grade energy we require to supply to run the pump, as well as that pump is consisting of number of moving parts. Though the number of moving parts which are available in the compressor are less as compared to are more as compared to pump, then also that pump is consisting of somewhat amount of number of moving parts. So because of that number of moving parts, there may be the chances of leakage of the ammonia refrigerant. And if ammonia will be leakage from the system, then it will have the as that ammonia is flammable gas, that's why it may be the hazardous. So here our main intention is to remove the pump. Our main intention is to remove the pump from aqua ammonia vapor absorption refrigeration system. So what will happen if I remove the pump? What will happen if I remove the pump? पंप जर रिमूव्ह केला तर काय होईल? पंप रिमूव्ह केला ह्याचा अर्थ काय झालं? इलेक्ट्रिसिटी सप्लाय करावं लागणार नाही आपल्याला ह्या ठिकाणी. त्या ठिकाणी जी काही हिटिंग कॉइल आहे, ह्या हिटिंग कॉइल थ्रू आपण हीट सप्लाय जरी केली, एक्झॉस्ट हीट जरी सप्लाय केली, तरी पण ही सिस्टीम वर्क होऊ शकते विदाउट यूज ऑफ इलेक्ट्रिसिटी. आणि सेकंड, त्या ठिकाणी मुव्हिंग पार्ट कुठं आहे का? त्या ठिकाणी पंप मध्येच फक्त मुव्हिंग पार्ट होता, दुसरीकडे कुठं मुव्हिंग पार्ट आहे का? नो. सो हियर by reducing the pump or by neglecting the pump or by escaping the pump, we can also make this system as a tight system which will not have a single moving part. Are you getting? So here what will happen here? The main purpose of using the pump is to increase the pressure from evaporating pressure to condenser pressure. कारण की ह्या ठिकाणी इव्हापरेटरच्या आउटलेटला प्रेशर कोणतं होतं? आपलं इव्हापरेटिंग प्रेशर होतं. इव्हापरेटिंग प्रेशर अमोनिया वेपर त्या ठिकाणी ऍब्झॉर्बर मध्ये आल्यानंतर त्यामध्ये आपण काय मिक्स करत होतो? इव्हापरेटिंग प्रेशरचं वीक सोल्युशन मिक्स करत होतो. आणि ह्या ठिकाणी ऍब्झॉर्बर मध्ये इव्हापरेटिंग प्रेशरचं वीक सोल्युशनचं कन्वर्जन स्ट्रॉंग ऍक्वा अमोनिया सोल्युशन मध्ये होत होतं. आणि ते इव्हापरेटिंग प्रेशर स्ट्रॉंग ऍक्वा अमोनिया सोल्युशन ज्यावेळेस पंपला देत होतो, त्यावेळेस त्या ठिकाणी ते प्रेशराइज करून इव्हापरेटिंग प्रेशरचं कन्वर्जन कशामध्ये करत होतो? कंडेन्सर प्रेशर मध्ये करत होतो. आणि या ठिकाणचा जो काय जनरेटर आहे, जनरेटर मध्ये पण काय करत होतो आपण? कंडेन्सर प्रेशरला ते जे काय ऍक्वा अमोनिया सोल्युशन आहे ते हीट करून त्या ठिकाणी जे काय अमोनिया वेपर आपण जनरेट करत होतो, त्या कोणत्या प्रेशरला करत होतो? कंडेन्सर प्रेशरला करत होतो. आणि जे काय राहिलेलं सोल्युशन होतं, वीक सोल्युशन, वीक ऍक्वा अमोनिया सोल्युशन, त्याचं प्रेशर काय होतं? कंडेन्सर प्रेशरच होतं. पण ह्या ठिकाणी कंडेन्सर प्रेशरचं त्या ठिकाणी कंडेन्सर प्रेशरचं कन्वर्जन परत इव्हापरेटिंग प्रेशर मध्ये करण्यासाठी आपण काय यूज करत होतो? त्या ठिकाणी प्रेशर रिड्युसिंग वॉल यूज करत होतो. सिमिलरली त्या ठिकाणी कंडेन्सरच्या आउटलेटला येणारं प्रेशर कंडेन्सर प्रेशर होतं, ते रिसिव्हरला दिलं, त्या ठिकाणी पण कंडेन्सर प्रेशर होतं. आणि ह्या ठिकाणी एक्सपान्शन वॉलच्या साहाय्यानं कंडेन्सर प्रेशरचं कन्वर्जन परत कशामध्ये करत होतो? इव्हापरेटिंग प्रेशर मध्ये करत होतो. बरोबर आहे? म्हणजे जर मला पंप रिड्यूस करायचा असेल, तर पंपच्या बरोबर मला काय रिड्यूस केलं पाहिजे? त्या सिस्टीम मधून हे प्रेशर रिड्युसिंग वॉल पण रिड्यूस केला पाहिजे आणि हा दुसरा प्रेशर रिड्युसिंग वॉल पण रिड्यूस केला पाहिजे. का? कारण की पंपचं फंक्शन काय होतं? टू इन्क्रीज द प्रेशर फ्रॉम इव्हापरेटिंग प्रेशर टू कंडेन्सर प्रेशर. टू इन्क्रीज द प्रेशर फ्रॉम इव्हापरेटिंग प्रेशर टू कंडेन्सर प्रेशर. दॅट वॉज द फंक्शन ऑफ पंप. And whatever pressure reducing wall or expansion wall we were using in that simple aqua ammonia system, so the purpose of that pressure reducing or expansion wall was to reduce the pressure from condenser pressure to evaporating pressure. was to reduce the pressure from condenser pressure to evaporating pressure. But as we are eliminating the pump, that's why at the time of or at the same time, along with pump, I have to eliminate the pressure reducing valve as well as expulsion valve also. Manje, in case of in case of Electrolux refrigeration system मध्ये काय असणार नाही, पंप पण असणार नाही आणि प्रेशर रिड्युसिंग वॉल्व पण असणार नाही. बाकीचे जे काय पार्ट आहेत ते बाकीचे पार्ट ऍज इट इज राहतील. बाकीचे पार्ट काय राहतील, ऍज इट इज राहतील. So this will be the diagram of Electrolux refrigeration system. This will be the diagram of Electrolux refrigeration system. We'll proceed further from the absorber. We'll proceed further from the evaporator. आपला evaporator आहे. evaporator मध्ये काय होणार आहे, कॉन्स्टंट प्रेशरला हीट ऍडिशन होणार आहे आणि कॉन्स्टंट प्रेशरला हीट ऍडिशन झाल्यामुळे त्या ठिकाणी आउटलेटला काय मिळणार आहे, पेपर रेफ्रिजरंट भेटणार. तो पेपर रेफ्रिजरंट आपण कशाला देत असतो, ऍब्झॉर्बरला देतो. त्या ठिकाणी हा आहे ऍब्झॉर्बर. आता ऍब्झॉर्बरचं कन्वर्जन किंवा ऍब्झॉर्बर मध्ये जे काही ऍक्वा अमोनिया सोल्युशन आहे ते आपण कशाला द्यायचं, जनरेटरला द्यायचं. पाठीमागच्या सिस्टम मध्ये काय केलं होतं, ऍब्झॉर्बरचं जे काही फ्लुइड आहे ते जनरेटरला देण्यासाठी ह्या ठिकाणी काय यूज केलं होतं, पंप यूज केला होता. पण या ठिकाणी आपल्याला पंप यूज करायचा नाही. या ठिकाणी पंप यूज करायचा नाही. जनरेटरला काय करणार आहे, आपण हीट देणार आहे. जनरेटरला हीट दिल्यामुळे काय होणार आहे, जे काय ऍक्वा अमोनिया सोल्युशन आहे त्या ऍक्वा अमोनिया सोल्युशन मधलं अमोनियाचं पेपरायझेशन होईल आणि ती पेपर अमोनिया आपण कशाला देतो, कंडेन्सरला देतो. कंडेन्सर परत इव्हापरेटरला देतो. पण ह्या ठिकाणी जे काही वीक ऍक्वा अमोनिया सोल्युशन राहणार आहे ते वीक ऍक्वा अमोनिया सोल्युशन ऍब्झॉर्बरला देताना ह्या ठिकाणी प्रेशर रिड्युसिंग वॉलची गरज नाही. ऍट द सेम टाइम इन बिटवीन कंडेन्सर आणि इव्हापरेटर त्या ठिकाणी पण प्रेशर रिड्युसिंग वॉलची गरज नाही. म्हणजे ज्यावेळेस आपण पंप रिमूव्ह करतोय किंवा पंप इलिमिनेट करतोय तर पंप इलिमिनेट करत असताना प्रेशर रिड्युसिंग वॉल्व इन बिटवीन जनरेटर अँड ऍब्झॉर्बर as we are eliminating the pump which is situated or located between the absorber and generator. So along with pump we have to also eliminate the pressure reducing valve which was situated between generator and absorber. At the same time we have to also eliminate pressure reducing valve or expansion device which is situated or located between condenser and evaporator. समजतंय? तर आता ह्या सिस्टीमचं वर्किंग कसं होणार आहे. सो आय विल टेल द वर्किंग प्रिन्सिपल ऑफ दिस सिस्टम. सो हियर वी आर युजिंग द थ्री फ्लुइड. Out of that first fluid is nothing but ammonia. And here ammonia is being used as a refrigerant. That's why whatever flow of ammonia will be there, that flow of ammonia will be throughout all the system. Flow of ammonia जो असणार आहे तो काय असणार आहे, throughout all the system असणार आहे. Then as an absorbent or as the absorber we are using the water. So whatever flow of water will be there, that flow of water will be only limited. From absorber to the generator and from generator to the absorber. So flow of water will be only limited from absorber to generator and generator to water. And why we are using the water as the absorbent? Because as a refrigerant we are using the ammonia, and water is having the tendency to absorb more and more amount of ammonia vapor. That's why along with ammonia water is the suitable absorbent. Are you getting? Then third fluid which we are using, that is nothing but the hydrogen. So that hydrogen is an inert gas. And also we are knowing that hydrogen is having the light weight. and also hydrogen is not soluble or not dissolvable in the water. Hydrogen water soluble nahi, or hydrogen cannot dissolve inside the water. That's why we are using third fluid as a hydrogen. That hydrogen can be used as a catalyst. आता ह्या ठिकाणी हायड्रोजन घ्यायची गरज काय पडली कोण सांगेल? Why we have to use the hydrogen? So whatever flow of hydrogen will be there, so that flow of hydrogen will be only limited to the evaporator to the absorber, and from absorber to the evaporator. So flow of hydrogen will be only limited to evaporator to absorber, and again absorber to evaporator. Flow of water will be limited to absorber to the generator, and from generator to the absorber. Whereas flow of ammonia, which is used as a refrigerant, that is throughout all the system, that is from absorber to generator, generator to rectifier, rectifier to condenser, condenser to evaporator, evaporator to again absorber. Are you getting? आता ह्या ठिकाणी हायड्रोजनची गरज काय पडली कोण सांगेल? Why there is a necessity of using the hydrogen as an inert gas or as a catalyst? Can anyone tell me? Okay, you might be knowing the basic. Why we are using the high pressure to the condenser side, and why we are using the low pressure to the evaporator side? Can anyone tell me? What is the purpose in case of VCRS system, as well as in case of simple aqua ammonia vapor absorption system also? We are using the two pressure. One is the high pressure, second one is the low pressure. So always we are supplying the high pressure to the condenser, and always we are supplying low pressure to the evaporator. Always we are supplying high pressure to the condenser, always we are supplying low pressure to the evaporator. So can anyone tell me why we are supplying higher pressure always to the condenser side and lower pressure always to the evaporator side? कोण सांगेल? Because our main intention is to reject the heat in case of condenser. कंडेन्सर मध्ये आपल्याला काय करावं लागते? हीट रिजेक्ट करावं लागते, आणि हीट रिजेक्ट केल्यामुळे आपल्याला काय करावं लागते? त्या ठिकाणी पेपरचं कन्वर्जन लिक्विड मध्ये करावं लागते. पेपरचं कन्वर्जन लिक्विड मध्ये करावं लागते. आता जर एखाद्या रेफ्रिजरंटचं पेपरचं कन्वर्जन जर लिक्विड मध्ये करायचं असेल, तर त्या ठिकाणी ते इझिली पेपरचं कन्वर्जन लिक्विड मध्ये होण्यासाठी आपल्याला काय करावं लागणार आहे? त्या लिक्विडचा किंवा त्या रेफ्रिजरंटचा बॉइलिंग पॉईंट टेम्परेचर वाढवावं लागणार आहे. आणि जर बॉइलिंग पॉईंट टेम्परेचर वाढवायचं असेल, तर जसजसं मी प्रेशर वाढवेल तसं त्या लिक्विडचा किंवा त्या रेफ्रिजरंटचा बॉइलिंग पॉईंट टेम्परेचर वाढणार आहे. बरोबर? म्हणून कंडेन्सरला मी नेहमी हायर प्रेशर का देतो? कारण की हायर प्रेशर दिल्यामुळं त्या रेफ्रिजरंटचा जो काय बॉइलिंग पॉईंट टेम्परेचर आहे, तो रेफ्रिजरंटचा बॉइलिंग पॉईंट टेम्परेचर वाढतो, आणि रेफ्रिजरंटचा बॉइलिंग पॉईंट टेम्परेचर वाढल्यामुळे काय होते? त्या ठिकाणी इझिली पेपर रेफ्रिजरंटचं कन्वर्जन लिक्विड रेफ्रिजरंट मध्ये होते. पेपर रेफ्रिजरंट कन्वर्जन लिक्विड रेफ्रिजरंट मध्ये होते. आणि इव्हापरेटर मध्ये काय डिझायरेबल असतं? इव्हापरेटर मध्ये काय डिझायरेबल असतं? आपल्याला लिक्विडचं कन्वर्जन पेपर मध्ये करायचं असतं. इव्हापरेटर मध्ये लिक्विडचं कन्वर्जन पेपर मध्ये करायचं असतं, आणि त्यासाठी आपल्याला त्या रेफ्रिजरंटला हीट ऍब्झॉर्ब करावं लागत असतं. आता जर लिक्विडचं कन्वर्जन पेपर मध्ये इझिली करायचं असेल, आता एक्झाम्पल घ्या ना तुम्ही. 1 atmospheric प्रेशर कन्सिडर केलं, तर 1 atmospheric प्रेशरला वॉटर किती डिग्री सेंटीग्रेडला बॉईल होतं? 100 डिग्री सेंटीग्रेडला बॉईल होतं. बट सेम वॉटर कॅन बॉईल ॲट अ 6 डिग्री सेंटीग्रेड also. Same water can boil at a 6 degree centigrade also, but we have to maintain the pressure. We have to maintain the pressure as a factory pressure. जर आपण 5.6 सेंटीमीटर ऑफ वॉटर कॉलम जर प्रेशर घेतलं, 5.6 सेंटीमीटर ऑफ वॉटर कॉलम जर प्रेशर घेतलं, म्हणजे निगेटिव्ह प्रेशर जर घेतलं, तर निगेटिव्ह प्रेशरला त्याचा बॉइलिंग पॉईंट टेम्परेचर कमी होतं. सेम प्रिन्सिपल इज यूज्ड इन केस ऑफ रेफ्रिजरेशन also. So here, in case of evaporator, we require to convert liquid refrigerant, or we require to convert liquid refrigerant into vapor refrigerant easily. And for easy conversion of liquid refrigerant into vapor refrigerant, we require to reduce the pressure. We require to reduce the pressure because at lower pressure boiling point temperature of that refrigerant will also go on decreasing. So that was the main purpose. That was the main purpose of providing higher pressure to the condenser side and providing lower pressure to the evaporator side. But here in case of three fluid refrigeration system or in case of Electrolux refrigeration system, as we are not using the pump, hence pressure throughout the system will be same. Pressure throughout the system will be same. So here if I'm considering pressure inside the condenser as a condenser pressure or PC, so same pressure will be applicable inside the evaporator. कारण की ह्या ठिकाणी प्रेशर रिड्युसिंग वॉल आहे का किंवा प्रेशर इन्क्रीज करतोय का किंवा डिक्रीज करतोय का नाही. As it is that ammonia liquid is getting will be given to the evaporator, so here also pressure will be equal to condenser pressure. ह्या ठिकाणी ज्या काही वेपर जनरेट होतील त्याचं पण प्रेशर काय राहणार आहे, कंडेन्सर प्रेशर एवढंच राहणार आहे. सेम प्रेशर ह्या ठिकाणी पण काय राहणार आहे, कंडेन्सर प्रेशर एवढंच राहणार आहे. सेम प्रेशर ह्या ठिकाणी पण राहणार आहे, कंडेन्सर प्रेशर एवढंच. आता तुमचा फर्स्ट क्वेश्चन काय असू शकतो, सर त्या ठिकाणी ऍब्झॉर्बर मध्ये पण प्रेशर काय, कंडेन्सर प्रेशर आहे आणि जनरेटर मध्ये पण प्रेशर काय, कंडेन्सर प्रेशर आहे. तरी पण त्या ठिकाणी फ्लो ऑफ रेफ्रिजरंट किंवा फ्लो ऑफ लिक्विड ऍब्झॉर्बर टू जनरेटर कसा होतो, कारण की ह्या ठिकाणी इन बिटवीन ऍब्झॉर्बर टू जनरेटर आपण पंप यूज करत नाही किंवा दुसरं अनदर डिव्हाइस पण यूज करत नाही, तरी पण फ्लो ऑफ रेफ्रिजरंट कसा होतो. तर ह्या ठिकाणी जो काय फ्लो ऑफ रेफ्रिजरंट होणार आहे तो कशामुळे होणार आहे, दॅट विल बी मेनली बिकॉज ऑफ कॉन्सन्ट्रेशन डिफरन्स. That will be mainly because of concentration difference only. Because what will happen here, whatever weak aqua ammonia solution will be there, that weak aqua ammonia solution will be supplied to the absorber, and inside the absorber whatever ammonia vapor as well as hydrogen is coming, so out of that ammonia vapor and hydrogen, ammonia will be absorbed by that weak aqua ammonia solution, and because of absorption of ammonia, here weak aqua ammonia solution will become as a strong aqua ammonia solution. And as hydrogen is insoluble inside the water, that's why that hydrogen will get escaped, that will be again supplied to the evaporator. Now here as we are having the strong aqua ammonia solution, and here we are having the, as we are supplying the heat continuously, that's why here continuous conversion of ammonia liquid into ammonia vapor is taking place. That's why here always we will have the weak aqua ammonia solution. So here because of concentration difference between strong aqua ammonia solution to weak aqua ammonia solution, the flow of solution will take place from absorber to generator, and whatever flow of refrigerant or flow of solution will take place from generator to absorber will be there, that will be mainly because of gravity difference, because here generator is at higher position and absorber is at lower position. That's why because of gravity difference, that flow of refrigerant will take place from weak aqua ammonia solution to strong aqua ammonia solution. Second thing, here now here pressure inside the condenser is same as well as pressure inside the evaporator is same. Try to use the hydrogen. Hydrogen is used as a catalyst. Catalyst means to increase the rate of evaporation of ammonia vapor, or to increase the rate of evaporation of ammonia, we are using the hydrogen as a catalyst. How that hydrogen is acting as a catalyst? So here inside the condenser, whatever pressure is there, that is nothing but condenser pressure. But inside the condenser only ammonia is present. Inside the condenser only ammonia is present. That means whatever condenser pressure is there, that condenser pressure is nothing but the pressure of ammonia vapor. Pressure of ammonia vapor. Pressure of ammonia vapor. And here, when that ammonia liquid will come to the evaporator, so inside the evaporator, we are mixing the hydrogen gas. We are mixing the hydrogen gas inside the ammonia liquid. And because of mixing the hydrogen gas inside the ammonia liquid, whatever pressure will be there, here evaporator pressure or pressure inside the evaporator will be same, that is condenser pressure. But according to Dalton's law of partial pressure, as inside the evaporator, whatever total pressure is there, that is mainly because of ammonia and hydrogen. That's why here this entire pressure or this total pressure is nothing but it is the partial pressure or addition of partial pressure of ammonia. Plus partial pressure of hydrogen. आता ह्या ठिकाणी जर प्रेशर बघितलं, कंडेन्सर मध्ये काय होतं, 100% अमोनियाचं प्रेशर होतं आणि इव्हापोरेटर मध्ये ते काय झालेलं, कमी झालेलं, पर्सेंटेज कमी झालेलं. म्हणजे ह्या ठिकाणी ऑटोमॅटिकली वी हॅव रिड्यूस द प्रेशर ऑफ रेफ्रिजरंट. though the total pressure is same, then also we have reduced the pressure of refrigerant, and because of reducing the pressure of refrigerant, त्या ठिकाणी आपण अमोनियाचं पार्शियल प्रेशर कमी केल्यामुळे काय होतंय, त्या ठिकाणी इझिली तो अमोनिया लिक्विडचं कन्वर्जन कशामध्ये होणार आहे, अमोनिया वेपर मध्ये होणार. That's why that hydrogen will be called as a catalyst. We are using the hydrogen, or we are calling it hydrogen as a catalyst because of addition of hydrogen inside the ammonia in the evaporator. The partial pressure of ammonia or partial pressure of refrigerant is being reduced, and because of reduction of partial pressure of refrigerant, boiling point temperature of that ammonia will also goes on decreasing, and because of decreasing the boiling point temperature of ammonia, that ammonia will now easily convert from liquid to vapor. That's why we are calling ammonia as a hydrogen as a catalyst. So this entire system will be called as a Electrolux refrigeration system or three-tube vapor absorption refrigeration system. Have you understood this system? Yes or no? So within 2 minutes, I will explain the flow of refrigerant or flow of the system. So what will happen? As at the outlet of condenser, सुरुवात मी इथून करतो त्या ठिकाणी किंवा इथं कंडेन्सर पासून सुरुवात करतो. कंडेन्सरच्या इनलेटला काय आपल्याकडे हाय प्रेशर अमोनिया वेपर आहे. हाय प्रेशर अमोनिया वेपर काय करतील, ह्या ठिकाणी कंडेन्सर मध्ये कॉन्स्टंट प्रेशरला हीट रिजेक्ट करतील. कॉन्स्टंट प्रेशरला हीट रिजेक्ट केल्यामुळे अमोनिया वेपरचं कन्वर्जन कशामध्ये होणार आहे, अमोनिया लिक्विड मध्ये होणार आहे. आणि ते अमोनिया लिक्विड कशामध्ये असणार आहे, हाय प्रेशर मध्ये असणार आहे. आता ते हाय प्रेशर अमोनिया लिक्विड आपण कशाला सप्लाय करतोय, इव्हापोरेटरला सप्लाय करतोय. So whenever that high pressure ammonia liquid will come to the evaporator, inside the evaporator we are mixing the hydrogen gas. So because of mixing the hydrogen gas inside the ammonia liquid, the partial pressure of ammonia liquid will goes on decreasing, and because of absorption of small amount of heat also, here that ammonia liquid will get converted, or ammonia liquid will easily get converted into ammonia vapor. So at the outlet of evaporator, we will have the ammonia plus hydrogen vapor. Now that ammonia plus hydrogen vapor will be supplied to the absorber. So here, from one of the end we are supplying the weak aqua ammonia solution. To the absorber. So when that weak aqua ammonia solution will come in contact with the ammonia and hydrogen vapor, so out of that ammonia and hydrogen vapor, ammonia vapor will be absorbed. By weak aqua ammonia solution, and because of that weak aqua ammonia solution will get converted into strong aqua ammonia solution. As hydrogen is insoluble in water. That's why that hydrogen gas will get escaped from the absorber, and that will be again supplied to the evaporator. Now whatever that strong aqua ammonia solution will be there, that will be supplied through this heat exchanger, that will be given to the generator. Here we are providing the heat with the help of gas burner to that generator. So from that strong aqua ammonia solution, ammonia liquid will get vaporized, and that high pressure ammonia vapor will be supplied to the condenser, through rectifier, and whatever remaining weak solution will be there, weak aqua ammonia solution, that will be supplied to the absorber after passing through the heat exchanger. So likewise, this process will take place. So have you understood this Electrolux refrigeration system? Have you understood? Yes or no? Yes or no? Write in the chat box. Okay. Now, as the time is over, so we are going to end our lecture here. So I will take the attendance. Wait for 1 minute. From the participant list, I will take the attendance. So roll number 1 present, 2 absent, 3 absent, 4 absent, 5 absent. Roll number 6 present, 7 absent. Roll number 8 present, 10, 9 absent, 10 absent, 11 absent, 12 absent, 13 absent, 14 absent, 15 present, 16 present, 17 absent, 18 present, then 19 absent, 20 absent, 21 present, 22 absent, 23 absent, 24 absent, 25 present, 26, 27, 28 absent, 29 present, 30 absent, 31 absent, 32 absent, 33 absent, 34 present, 35, 36, 37, 38, 39 absent. Roll number 40 present, 41 absent, 42 present, 43 present, 44 present, 45 present, then 46 absent, 47 present, 48 absent, 49 present, 50 present, 51 present, 52 absent, 53 absent, 54 absent, 55 absent, 56 absent, 57 absent, 58 present, 59 absent. Roll number 60 present, 61 absent, 62 present, 63 absent, 64 present, then 65 present, 66 absent, 67 absent, 68 absent, 69 present, 70 absent, 71 present, 72 present, 73 present, then 74 absent, 75 absent, 76 absent. Roll number 30 is also present. Then roll number 61 is also present. Then roll number 68 is also present. Apart from this, is anyone remaining to do the attendance? If not, you can exit the lecture.